Bismillah ar-Rahman ar-Rahim. Today inshallah we are going to do a Hysys tutorial about the distillation, and our doctor is Naif Muhammad Jassim in the United Arab Emirates University from Chemical Engineering Department. Okay, here is now the worksheet which discuss and explain the distillation issue that we are going to use it in Hysys, this icons. Okay, now we will start with a new sheet about the distillation column. So now the following example builds a shortcut column. So our column or the distillation column is shortcut as a the preponizer having the stream feed as the tower feed. Now the feed is here is the specification of the feed, temperature, pressure, and the flow rate or the molar flow rate, yeah. And the composition and mole fraction also is mentioned here. So now first of all we are going to add the component of the distillation column. So we go to Hysys here, we add the component. Okay, we have ethane and propane, and also you have isobutane. And we have also N-butane, and you have also again we have here I-pentane, and N-pentane. What else do we have? And we have N-hexane also. Hexane, yeah. Okay, now we can, and here's the mole fraction of each component. So we go to here and we, as you can see, we add all of them. Now we close this one. Close it, and now we have to add the fill with package. Now as we said, we are going to add the fill with package from add. Now we choose the best fill with package for distillation column is in RTL. In RTL it's here. We add it now, we close it now also, so it's here. Now it's ready, yeah? So we have to add the shortcut column, and here's the shortcut distillation column. We drag it to here. So we press Ctrl, then we drag the streams outside, and if you want you can go here and you can name them as you like. But anyway, and also here for the heat can take them out also for the cube. So now we add the component in the feed. So from the worksheet you can see now the specification of the feed, now temperature, okay, now temperature is 207.3, pressure 100 psi absolute, it's here, yeah. And also now the molar flow rate, it's 100. as you can see it here, it's not it's yes. And the component, now we of course we add the composition of the feed, and it's here. You can press any number, for example, then you delete it. Okay, now we choose now the mole fraction. As we can see here, it's in mole fraction. It's in mole fraction, so we add them slowly in mole fraction. We have 0.148, and you have to be sure that the total of all of the compositions fraction should be equal to 1. Now we press OK, and now it's ready. So we close it and we come here. So now we have to press on the column now here. So we go to parameter. Now here we go to parameter. We have the right key in bottoms and heavy key in distillate. We go to the distillation or the worksheet. You can see here distilled is ibutan, which is 0.02 mole fraction, and the right key in the bottom is propane, 0.025 mole fraction. So we go here. So what's the right key in the bottom? The right key in the bottom is propane. So we add propane. Right key in the bottom is propane, and we of course we add the ratio or the fraction, mole fraction of the propane in the bottom, 0.05. And for the heavy key, which is ibutan, which is ibutan, which is ibutan, we go here, choose ibutan, and we enter the mole fraction of it, which is 0.02. Now the pressure that we hear, we enter the same pressure of the feed, which is 100 psi gauge. Should do it. As we can see here, the warning, unknown pressure, and the same way for here also. This one 100 also psi gauge, psi atmosphere or absolute. And now if you are asked about the minimum reflux ratio is 0.798, and the external reflux ratio should be always equal or more than this ratio. So now it's done, and let's go to the worksheet. And the reflux ratio is said mole fraction, where the reflux ratio is 1.5, so it's more than this one, so it's available. Now everything is done and it's ready, so we close this one, and we can see here the feed. And he said calculate the maximum reflux ratio and column performance. So the minimum reflux ratio from parameters, it's here 0.798, and we go to the performance, and also here you can see the minimum number of trays, 6.244, the actual number of trays also, the optimal feed stage, everything is mentioned here from the performance. So we can the overhead stream, and we can say show table. There's them, and here the same way, and now it's here, and you should ensure that it's solver. Okay, it's active. The solving icon is active. So now this is the distillation column shortcut briefly, and how it could be done. Now we can go to the second problem or second issue about distillation column with another distillation column problem. Let's mention here the component and the specification of temperature and pressure. Now we can go to the same way. We can do the same way by the following. Yes, this is new, and we add the component. We have here benzene and toluene. We add the component, also the fluid package, same way in RTL. We enter the solution column, it's here. It's fine, we choose shortcut column, which is here. We drag the streams out and in. Also for the heat streams, we can drag them out. And now we add we go to see the specification. Here we have the temperature, or we have the pressure. 0.32 kilopascal. For the molar flow rate, it's here 100 kilomole per hour. Choose 100 kilomole per hour. It's already here. And for the composition, we choose 0.5, and the same way we choose molar fraction because the molar flow rate in 100 kilomole per hour. So 0.5 the same. It's 1. Okay, press OK. Now the temperature, we go to, it's not written the temperature, but we can see the feed is liquid at the boiling point. So what does that mean? That means that the vapor phase pressure, vapor phase fraction is 0. There is no vapor. So now it's okay. And here is the temperature of the boiling point of the mixture. Now we go to the shortcut column. Here we go to the parameter. We go to the problem now. We can see here he said the distilled is that means in the distilled contain mainly of 90% of benzene. So that means the light key is benzene. So we go to the column here. So parameter, the light key in the bottom, which is the benzene, which has the lowest fraction in the bottom, 0.1. So we choose here. We choose benzene and 0.1. And the heavy key in the distilled should be the toluene. And how much the fraction should be 0.1, also the same. 0.1 because in the it's 90% of benzene in the distilled. So now the reflux ratio is 4.52. 521. This is just wrong. 5.21. So we can, but first of all we should mention the pressure here. It's 101.32 kilopascal. The same way. 32 kilopascal plus. Now here is the minimum reflux ratio. Should be 0.81. Now what did he say? Number of theoretical trays needed. So we should add the reflux ratio 4.521. Now we can see it's solved. So we go to, here's the stream, and here's the molar flow rate for the overhead stream and the bottom stream. And now you need also the number of theoretical trays needed. We go here and we go to performance, and we can see here the minimum number of trays is 4.628. Here is now the answer 50, that is still 50, and also the bottom down is 50. Here is now it's here should be 4.6, 4.6, yeah, 4.62. That's all. Theoretical. We are going to move in the continuous. Number 3, it said repeat problem 2, but use the feed that is saturated vapor. That means the vapor fraction is 1 at the following. Minimum reflux ratio, the minimum number of theoretical plates at the total reflux. We can go here, it's the same way, we don't change anything. Just we go to the feed, we press this one equal to 1, and that's fine. Go here, parameter, we can see that the minimum reflux ratio is 1.829, and he said the minimum number of theoretical plates, or the plates at the same trays, same as trays, at the total reflux, go here, performance, here is the minimum number of trays, it's here, or the theoretical, yeah. Now we have, he said the theoretical number of trays at an operating reflux ratio 1.5 of the minimum reflux ratio. So we multiply 1.5 times the 0.8 or times 1.829, and that's 2.74. So we do that and it's ready. We go to the performance, and you can see here the actual number of trays with our reflex ratio. It's here. Theoretical number of trays at an operating reflex ratio 1.5. That means the actual number of trays. So now the fourth problem is about the continuous distillation column. So now here is the feed and the specification for the feed, and also here is the component. So we can start with a new problem. Here's a new, we add a component. What do we have? We have here now the component are ethanol, isopropanol. So ethanol, isopropanol, they are done. The fluid package we added an RTL. We enter the simulation environment. Now here is the distillation column. Here is the continuous distillation column. You can drag the streams. So now total distillation column. So we have here overhead. You can do it over the distill. You can name it. I prefer to do that. Atom. Here is Q bottom, and here is Q distill, and here is the feed. You can name it feed to be more next. So before that we go here. Here is now the component and the mass fraction of them, and here is he said now assume number of trays to be 24. So now so the number of trays is 24. Here is the trays or the stages or the plates. We write 24 and everything is okay. Now we press next. We have the pressure. We choose the same pressure, 1 atmosphere pressure. 1 atmosphere, same pressure. Atmosphere. We press next. Temperature also the same, 25 degrees Celsius. Here 25 also. We don't care for this one. So we have here next. We have here now the reflux ratio equal to 3. So do here 3. We leave this one and this one, and we say no, done. Now here is the icon of the distillation column. So when we now we go to the monitor, it's here, and we can see here now because we don't have them. So now it's uncovered. So what do we have to do? Let's go here. We said find the condition of exit stream. Firstly, we enter the condition of the feed. Temperature 25 Celsius, it's 0 atmospheric pressure, and the molar flow, the mass flow rate, it's 163. It's mass flow rate. Pound per hour, and we go to the composition. It's 50-50 in mass fraction, so we put here 0.5. We can see here it's in mole fraction, so we change it to mass fraction, 0.5, and now it's ready. It's okay, so we close it. Now we go here, we return here. It says suppose that the heat and also now it's for the reboiler heat duty of 1200, 1020 or 120,000 BTU per hour. So we go to the monitor specification. We choose column duty because the temperature that we have or the heat that we have, it's heat duty of what? Of the reboiler. So it's here duty. We choose Q reboiler from down, and here we enter the value, the heat, and the unit BTU per hour. We should go to the parameter here, and here the temperature we should remove it because we don't know the temperature in the distilled or in the bottom. We make wrong first in the middle and we put the temperature is 25. So now we go back to the design or then monitor, and here you can tick on specification here, and you can see it's covered. So and here is also it's running. You can see run, it's covered, and here is everything is done. Here you can show table of the result. same way for this one. Show table also. Here's also the same. And now this is the continuous shortcut, continuous distillation column. Now let us go to. Now suppose that the heat duty of the boiler is not given. Can it be solved? Of course no, because look here. Here, if we go to the monitor and we don't have this one, the degree of freedom it's 1, so it can. And what about the other one? Now we go to the number B. He said if the fraction of ethanol is in the distilled is 0.7, calculate the boiler and condenser heated duty. So what we are going, we remove this tick from heated duty, we add specification, we choose column component fraction. Now he said the ethanol in the distilled, so that means it's ethanol in the distilled, which is in the condenser, and because in the condenser it condensed and it's in liquid phase, so it's liquid here, and here is we leave the mole fraction, we enter 0.7. Now the component is ethanol, so we choose ethanol, and now we can see it covered, and everything is done. So we go to the, here's the heat duty for the reboiler, and here's the heat duty for the condenser, QC and QR. And thank you for listening. If you have any questions, we are ready to answer you, and inshallah just be wait for the next tutorials about Hysys and the application of chemical engineering department using Hysys program. And thank you for watching, and please comment on on my work, and thank you so much. Thank you.